Before we jump into how to do this with complex numbers, I tend to find that factorizing by completing the square tends to need a little bit of revision before we can just jump straight in. So let's just quickly go across and walk through why this works with quadratics. Okay, so something like x squared plus 6x plus 9 is a perfect square. If I factorize this, my factors are going to be x plus 3, x plus 3, which I can simplify as being x plus 3 all squared. The reason why this is a perfect square is because I need two numbers that multiply to give 9 and add to give 6. Well, the only two numbers that do that is 3 and, surprise, surprise, 3 again. So if 3 plus 3 is going to combine together to give 6, then essentially the idea that forms here is, well, if I halve whatever my b term is, which in this case here is 6, if I halve my b term and I square it, I'm always going to find the number I need to add to any quadratic to make it a perfect square. And what I mean by that is, if I just pull this down here, is if I have something like x squared plus, let's do 8x, and I want to figure out, hey, what can I add to x squared plus 8x that's going to give me a perfect square? Well, all I have to do is simply just halve my b value. Well, in this case, b is always the term in front of just my x term. So in this case, b is equal to 8. So if I halve b, I'm halving 8, I'm going to get the number 4. Half of 8 is 4. If I square 4, I get the number 16. So if I add the number 16 to the expression x squared plus 8x, I have now created a perfect square. The little catch to this method is that I can't just add numbers randomly into a quadratic or some kind of complex quadratic like we're trying to solve. If I add something in, I need to balance my equation. Okay, so let's say x squared plus 8x is going to be equal to 0. If I add 16 to one side of my equation, in order to balance my expression, I need to also add 16 to the other side. Now, if I rearrange this to get everything on one side, because I want my whole expression to equal 0, because I'm trying to do some kind of solving or some kind of solution, then to rearrange this, I simply just subtract 16 from this side, and I need to also subtract 16 from this side. So typically when we're completing the square, we get this situation here, which is plus 16 minus 16. Now, obviously these two terms cancel out. So the point of doing this is I haven't actually changed my question. Plus 16 minus 16 is equal to 0. The math still balances. However, if I now group my first three terms together, I have a perfect square, and I can now factorize this quadratic with a perfect square as a part of my solution. So to keep working with this example, this would equal, well, x squared plus 8x plus 16 is a perfect square. I know that 4 times 4 is equal to 16. 4 plus 4 is equal to 8. So then my first bit is going to become x plus 4 all squared minus 16. That would be a solution to my quadratic. This also puts things in turning point form, which for quadratics specifically can be quite useful. And we'll just ignore this little bit at the end. I thought it was going to be useful, but it kind of wasn't. I think we get the general idea. I think we've recapped this enough. I'm going to do the same process now, except instead of having x's, I'm going to have z's. So let's come back to our complex quadratic. Okay, I have my complex quadratic. Now with my complex quadratic, the difference here is I actually have a number in front of my z. I have a 2. Well, it's kind of not what I had in my example I did with quadratics. If I have a coefficient of x squared, or in this case, z squared, I actually can't complete the square. It doesn't really work. So I need to take my 2 out the front of my equation as a common factor. So my coefficient of z squared is simply just 1. If I do that, I'm going to get 2 outside of z squared minus, well, if I divide by 2, that's going to be 3 over 2z plus 2. That is my new quadratic. Now, if I look at my number in front of z, I don't see anything there, so I assume it's just 1 times z squared. My coefficient of z is just 1. Okay, happy days. I can now start working with my b's. In this question here, b is going to be equal to negative 3 over 2. And in the last example we looked at with quadratics, I said, okay, well, we're going to divide our b by 2. So I'm going to divide this whole thing by 2. And I'm going to square my term. So I'm going to square this term like so. Now, if I have a fraction and I'm dividing by a whole number, I can keep it, change it, flip it. So I can change this into a multiplication. That's going to become minus 3 over 2 times, if I flip 2, it's going to be times a half, and I'm going to be left with negative 3 over 4 all squared. This is now the term I want to add into my complex quadratic, and I also want to subtract from my complex quadratic. So if I keep working through this, this is going to become 2 brackets z squared. My middle term is going to stay the exact same. And now, let's use pink. I'm going to add this in minus 3 over 4 all squared. I'm going to add it in. I'm also going to take it away. So I'm going to subtract negative 3 over 4 all squared. Now, my little 2 part here on the end, that's just going to pop out at the end the exact same way. I'm just going to put a little plus 2 over here. And this is all going to go in brackets. So I've now manipulated my algebra. I've created a situation where if I look at this little section here, I have a perfect square. The reason why I left my pink bit in brackets and I kept my little squared part there is because it makes it really easy when it comes to the factorizing part. To factorize this, I can simply just do 2 outside of, well, z squared is going to become z. And whatever's inside my brackets here, if it's a negative, it's going to be a negative. If it's a positive, it'd be plus. I simply just write that number down here like so, and I'm going to square that entire set there. Now, I should put a little extra bracket in because everything is still being multiplied by 2. I now am going to clean up my kind of tail bit. That's going to be minus negative 3 squared is going to become 9. 4 squared is going to become 16. This whole term here is going to simplify down to nothing. It actually simplifies down to nothing. There's nothing in common, sorry. It looked really promising, but it's just going to stay as 9 over 16. Okay, and I'm going to add 2 to that whole thing. Again, close my brackets up. I still am trying to do some form of factorizing here. So I now want to add 9/16 to 2. I'm going to get some messy fractions here. We will be getting a lot of messy fractions when we do this completing the square process, but don't be frightened of the fractions. Just embrace them. You know, fractions are our friend. So we're going to now do, okay, I got 2 outside still. That's going to be, I might scroll down to have a little bit more space actually. Okay, I'm going to have 2 outside of z minus 3 over 4 all squared. And now I have negative 9/16 plus 2. Well, 2 is 32 over 16, right? Because 16 goes into 32 twice. So I have negative 9 plus 32. That's going to give, quick maths, 23. There we go. We got the 23 over 16. Oh, lovely. Absolutely beautiful stuff. Now, some of us may be able to see what I have here. Okay, if you remember the first example, we did the first concept, the sum of 2 squares. Well, I have a perfect square here, plus, not quite a perfect square by a long shot, but some number that I can put under a square root. So I'm going to turn this new and slightly weird sum, I have a sum of 2 squareds here. I'm going to turn this into a difference of 2 squares. Okay, so this is going to turn into 2 outside of z minus 3 over 4 all squared minus 23/16 I squared. Again, I'm turning this into a difference of 2 squares. This is my first term. I know it's got 2 numbers in it, but it's going to be considered as just one single term. And this here is my second term. This is going to equal 2 outside of, if I do my difference of 2 squares. If I take the square root of z minus 3 over 4 squared, that's just going to give z minus 3 over 4. And now I'm going to have plus the square root of 23 over 16i. I'm also going to have z minus 3 over 4 minus the square root of 23 over 16i. And guess what, guys? I've got fantastic news. I can actually keep trying to simplify this. So I can actually do 2 outside of z minus 3 over 4. And if I take the square root of the top, square root 23, that's just going to stay square root 23. But the square root of 16 is actually going to give me 4. So it's going to be plus the square root of 23 over 4 lots of I. Doing the same thing to my other bracket is going to give me the square root of 23 over 4 lots of I as well. So, like I said, it looks a little scary. I've got 3 terms inside my brackets, but it comes from the idea that I treat this as just one individual term, and I treat this as my second term. If I do that, the part inside my brackets, my perfect square bit, and this is going to be true for every time I complete the square to factorize my complex number, the part inside the brackets that's squared, that's just going to stay exactly the same, and it's going to pop in down here, and then I simply just plus or minus the square root of my second term that I have highlighted in yellow. So if the question just asks to factorize, I'm done, I don't need to do any more, that's full marks. However, if I'm asked to factorize and solve, well then I'm going to let each bracket equal 0 and solve it just like I did above. So that's going to become z minus 3 over 4 plus the square root of 23 over 4i is equal to 0. If I work through this algebraically, I'm going to get z is equal to 3 over 4 minus the square root of 23 over 4i. If I do the same to my other bracket, if I scroll down a little bit, if I do the same to the other bracket, that is going to be z minus 3 over 4 minus root 23 over 4i equals 0, which is simply going to give me z equals 3 over 4 plus the square root of 23 over 4i. So my 2 solutions is going to be this answer here and this answer here are going to be my solutions for my complex number z. You can see here in these parts, I have both a real component, I have a real component here, I have a real component here, and I have an imaginary component here on the end as well. So let's label this as being real for z. So this makes sense for my complex number. Z is equal to 3 over 4 minus the square root of 23 over 4i, both a real component and an imaginary component for my complex number z.